A clove bud weighs less than 0.1 grams. You can hold it between two fingertips and barely notice its mass, but if you bite directly into it, the experience is anything but light. Your tongue burns, then goes numb. Taste signals feel as if someone has pulled the plug. The brain struggles to distinguish sweet from salty. This is not an ordinary culinary moment. It is a biological defense system compressed into a tiny structure, and the plant that produces it, Syzygium aromaticum, was never trying to please humans. Let's take it apart like a finely engineered device to understand why a flower bud frozen mid-bloom can behave like a chemical grenade. Clove is not a seed or a fruit. It is an unopened flower bud, harvested at the precise moment just before blooming. At the threshold of its most intense growth phase, the process is abruptly interrupted. Why does that matter? Because during the pre-bloom stage, plants accumulate maximum nutrients and secondary compounds to protect their reproductive organs. Flowers represent the future of the plant, the site of pollination and seed formation. Losing a flower means losing the next generation. As a result, the plant concentrates its resources into the bud like a biological vault. When the bud is picked and dried, water, which makes up about 70–80% of its fresh weight, evaporates. What remains is a rigid framework of lignin and cellulose, enclosing a dense core of essential oil. Its nail-like shape is not just aesthetic coincidence. It results from the stem and calyx shrinking during dehydration, forming a compact structure that resists breaking during transport. We are not merely drying a flower. We are freezing a biological moment, preserving the plant's highest defensive concentration inside a natural capsule. That is why clove is not simply fragrant. It is intense, almost aggressive in its density. If clove were a device, its core component would be eugenol. This phenolic compound has the molecular formula C10H12O2. Its structure includes an aromatic benzene ring, the backbone of many biologically active molecules attached to a hydroxyl group, OH, and an AP allyl chain. The hydroxyl group allows eugenol to interact strongly with proteins and cell membranes. In clove essential oil, eugenol accounts for up to 80–90% of the composition, an extraordinary figure in the plant world. Most essential oils contain only a small percentage of a dominant compound. Here, it is like an elephant balancing on the head of a pin, one molecule dominating nearly the entire chemical space of the bud. At such high concentrations, eugenol creates enormous chemical pressure. When released, these volatile molecules rapidly disperse into the air and bind to receptors in the nose and tongue. A single clove can dominate an entire stew because each eugenol molecule strongly activates TRPV. One sensory channels the same receptors that respond to capsaicin in chili peppers. That is why cloves can easily overpower a dish when overused. You are not simply adding flavor. You are triggering a molecular-scale chemical reaction within your nervous system. Yet the strangest quality of clove is not its heat, it is the numbness. Eugenol can influence sodium ion channels in nerve cell membranes. Normally, when you bite into something hot or painful, these channels open, allowing Na- ions to rush in and generate electrical signals that travel to the brain. That is how pain is perceived. Eugenol acts like a quiet electrical technician. It alters the protein configuration of these ion channels, disrupting sodium flow. Neural signals weaken. Pain sensation is partially switched off. This mechanism is why clove became one of humanity's earliest dental anesthetics. Long before lidocaine was synthesized, dentists used clove oil to relieve toothaches, not out of superstition, but because eugenol's biochemistry genuinely numbs nerve endings. When you hold a clove bud in your mouth and your tongue starts to feel numb, you are witnessing a live biological experiment. Your ion channels are being modulated. Your nervous system is being chemically influenced. A tiny spice, behaving like a pharmacological agent. So why does Syzygium aromaticum produce so much eugenol in the first place? The answer has nothing to do with cuisine. It is about survival. In humid tropical environments, flower buds are prime targets for insects and microorganisms. Eugenol has strong antibacterial and antifungal properties because it can disrupt bacterial lipid membranes, causing ions and intracellular enzymes to leak out. For insects, the sharp aroma serves as a warning signal. This is not an easy meal. In other words, clove is a plant's no-entry sign. Humans, with adaptable taste systems, did something nature never anticipated. We hacked that defense mechanism. Instead of avoiding it, we diluted it, blending it with sugar, wine, meat, and baked goods. At lower concentrations, eugenol stops behaving like a weapon and becomes a warm, deep, and complex aroma. This reflects a universal rule of sensory chemistry. Dosage defines experience. At high levels, eugenol numbs and burns. At moderate levels, it gently stimulates and adds flavor depth. We did not domesticate clove by changing it. We domesticated it by controlling concentration. Clove was never created to flavor gingerbread or mulled wine. It is the product of millions of years of evolution, shaped by a plant's need to protect its reproductive organs from a world full of microbes and insects. Its eugenol-rich oil is a defense system compressed into a tiny form. A flower bud frozen at the perfect biological moment. A chemical core dense enough to numb nerves. And when we bite into it, we are not just tasting a spice. We are activating a biological mechanism designed to repel intrusion. Nature does not create aromas to comfort us. We simply learned how to use some of the most sophisticated chemical weapons in the plant kingdom and call them spices.